All right. So, here we are. I'm still getting exam 4 graded. My kid's daycare is conveniently closed today. So I will have them all this afternoon, but I will grade as quickly as possible. And then once I get them all graded, I will manually go in and update and switch your homework total for the lowest exam score. Okay, so it'll happen this weekend at some point. If you want to come pick up exam 4 for me next week, Monday, Tuesday, Wednesday, I might not just be in my office all day each of those days. So probably Monday and Wednesday for sure you can come by. For sure Monday. I might actually be there most of the day Monday. So Monday would be your best bet if you want to come by and get it. Probably Monday anytime throughout the day. Wednesday might be hit and miss. So if you're planning to come Wednesday, just email me and we can set a time. All right, let's get going on this. We'll take a break an hour in and then we'll finish up. You know, after that, we only have the room till 12. So got to be done by then. But I bet it'll take, goodness, I'm like sweating over here. I might, they don't have classes for a day, so they don't want to run the air. I don't know how long this will take us. So if I'm going too fast, just holler at me. This is super informal. So, all right, chapter 5 is where we're going to pick up. And this really only runs through chapter 9. I don't have review for chapter 10 specifically on here since that's the most recent thing we covered. But if you have questions on chapter 10, definitely feel free to ask. All right, chapter 5. So in chapter 5, we started writing, balancing, and classifying chemical reactions. Those were the 3 big things we did. So balancing, there was a few tips with balancing. You just have to have the same number of each kind of atom on both sides, right? One tip was save elements by themselves for last. And another tip was if polyatomic ions are present on both sides, you do not separate. For example, if I have sulfate, I'm not going to separate the S and the O and balance them separately. I just say, how many sulfates do I have on each side? Balance it that way. Classifying, I think balancing should have been kind of like the easier portion of chapter 5. Not that it's always super easy, but classifying chemical reactions tends to be a little more difficult. So the first 5 ways we learn to classify, we talked about synthesis reactions. That's where you have 2 or more things coming together. A plus B makes AB, all right? Or AB plus C makes ABC, something like that. Decomposition is the opposite of that. You have 1 or more things breaking down into 2 or 3 things. Single displacement is usually you have an element plus an ionic compound. Well, I'm not going to write ionic, but usually some kind of compound. Okay, it could be ionic or covalent. So, for example, that might look like this: A plus BC, where BC would be your compound. And displacement, A is going to displace something in BC. Now, it depends what A is. If A is a metal, I'm going to make a note over here. Metals displace cations. And then we said nonmetals displace anions. So if A is a metal, B is your cation, if this is an ionic compound, because cations are always written first, and we would get AC, and then B would be by itself. A has displaced B. But if A is a nonmetal, like oxygen or fluorine or chlorine, then it would displace C, okay? So this is written out if A is a metal. All right, double displacement, you have, where do I want to make a note of this? 2 ionic compounds is a key that you have double displacement. So that's A, B, plus C, D. And A is the cation in the first compound, so it's going to join up with D, the anion in the second compound. C is the cation in the second compound, so it's going to join up with B, the anion from the first compound. So they just switch. Combustion, you have some sort of carbohydrate, carbon joined up with hydrogen, and you could add, there's so many different carbohydrates, C3H8, C2H6, C4H10, CH4, okay? Some combination of carbon and hydrogen, and it's reacting with oxygen. Oxygen is a fuel, we know, for fires. And these always make carbon dioxide and water. All right, and then the 3 complex types of chemical reactions. So this is the first one we said, precipitation reactions. So what these are is you have 2 aqueous reactants. That's key there, 2 aqueous reactants. So for example, sodium chloride. And I'm gonna, on purpose, write AQ here, okay? Aqueous plus, let's say, ammonium fluoride. I don't know. Aqueous, 2 aqueous. I'm gonna highlight that. 2 aqueous reactants. Oh, I didn't think this through very well, because you're supposed to make a solid product. And ammonium and chlorides or sodium are always going to be aqueous. So let's just throw, let me change up one of these. We could do, it's going to be, oh, when chlorine is with lead, it makes a, so we'd say like lead nitrate. Lead 2 nitrate, so NO3 2. Okay. So when these make products, we're gonna need to shrink this down. These make their products. We're gonna have lead chloride, and this is gonna form a solid plus our, still don't have room, plus our sodium nitrate, which will still be aqueous. Okay. So 2 aqueous reactants making a solid product is a precipitation reaction. So if you don't start off with things that are both aqueous, then you can't really consider it a precipitation reaction if something's already solid on the reactant side or something like that. You'll have your solubility chart. That was kind of key in checking those things, especially if you aren't given the states of matter like AQ and S and stuff like that. If you are, then that's a pretty easy way to tell. All right, number 2, we talked about acid-base reactions. These should be fairly easy for you to spot now. If a hydrogen is transferred from one substance to another, it's acid-base, okay? So this is the transfer of hydrogen from acid to base in simplest form. When I first introduced it, I said anything that generally makes water, okay? But look, combustion reactions make water. They're not considered acid-base, so it's not always that's not always the way you can tell. But anytime a hydrogen is being transferred, then yes. Okay. And then the last thing we talked about was redox reactions. And this is when electrons are being transferred from one thing to another. So you have a change in oxidation states. So I'm not going to give you the rules for how to assign oxidation numbers. So make sure you review those and you're familiar. Remember, any element that's like by itself gets an oxidation number of what? 0. Anything by itself has 0. It's just neutral. We don't consider it to be electron rich or electron poor. So you assign zeros to anything by itself, and then you see how things change. Like really key signs that you have redox are like synthesis and decomposition. Look up here. We would give A an oxidation number of 0 and B an oxidation number of 0, but when they're in a compound, they're not 0. They're something else. Okay, and unless I specifically ask you, what's the oxidation number of this, in the compound, then you don't even have to go through and assign everything. You just immediately tell, oh, that's a redox reaction. Okay, if you're just like classifying. Same thing here. A and B would have oxidation numbers on the reaction side, but on the product side, for a decomposition reaction, we'd say there's 0. So definitely something's changing. That's all you need to know to classify it as redox, is something changing oxidation numbers. So I would say, I'm just going to put a note over here. Review rules for redox, or sorry, not for oxidation numbers. Do I actually have those? Oh, looky there. I was like, I think I actually do. So an atom in its elemental state gets an oxidation number of 0. Monatomic ion has an oxidation number equal to its charge. So there are some things that are always going to be predictable, like oxygen should always get an oxidation number of -2. Chlorine should always get an oxidation number of -1, stuff like that. But hydrogen can sometimes be like a +1 or a -1. It could do some weird things, okay? So not everything always matches its charge. But like oxygen's always predictable. Chlorine's always predictable. In a compound, an atom usually has the same oxidation number it'd have if it were an ion. And then the sum of the oxidation numbers in a neutral compound have to add up to 0. Okay. And then this last thing up here just says that solubility rules, how to apply them. You'll be given that chart. Just remember how to read that chart, which, do I have that down here? Yeah, here they are. Okay, here's the solubility chart. So just remember, anything on this side, the left side of the table, this says soluble at the top, which means anything that is soluble is aqueous. Okay. S does not stand for soluble. Anything that is an exception is going to be S, which means it will form a solid, and that is a precipitate. Okay. All right, let's go back up. I had some practice actually with redox. I think redox, would y'all agree, tends to be kind of the trickiest. So maybe that one deserves a little practice if we're going to practice at all. So which elements oxidize, which is reduced in the following reactions? Sign oxidation numbers. Okay. So we just read the rules for signing oxidation numbers. So go through, look at this first one. I'll do the first one with you, and then you can do one of these other ones by yourself. So Si, silicon here is by itself, give it a 0. Chlorine here is by itself, give it a 0. Now, I don't know what Si and Cl are just yet, but I know the sum of their oxidation numbers in this compound have to add up to 0. And you always have to take into account any subscripts. Like I have a subscript of 4 here on chlorine. So I have 4 chlorides, essentially. So I'm going to split this in half. And I know that the element that's written first gets the positive oxidation number. The element written second gets the negative oxidation number, just like cation and anion notation. So chlorine, what is chlorine if it's an ion? What's its charge? It's main group 7. It's a halogen. So it always has a charge of what? -1. So I'm going to give it an oxidation number that matches that. I'm going to give it a -1. Okay. And I've got 4 chlorines. So the total amount, when I add all those oxidation numbers for all 4 chlorines, comes out to be -4. Okay, so I'm going to write that underneath. The total is -4, which means the total amount of positive from the positive oxidation numbers has to add up to +4. Now I only have one silicon, right? I don't have a subscript on Si there. So that means the oxidation number for Si is +4. So now we just see what's changing. Silicon is going from 0 on the product side, it's a +4. Chlorine is going from 0 on the product side, it's a -1. I don't write that chlorine's a -4. That -4 is the sum of all 4 chlorines. Each chlorine has a -1. So I'm going to write that's going from 0 to -1. So what's being oxidized and what's being reduced? Do you remember how we defined each of those? Oxidation is the oil rig. Oxidation is, yeah, OIL. Oxidation is the loss of electrons. Reduction is the gain of electrons, oil rig. So which one's losing electrons? Chlorine? Chlorine is becoming more negative. Its oxidation number is being reduced. So silicon is oxidized. If you're losing electrons, you're becoming more positive. You're giving away things that are negatively charged. And so chlorine is reduced. Okay. All right, why don't you try, number 2. All right, maybe we can start looking at this. Who's got a suggestion on number 2? What should I do? Which one's a 0? Yep. Good. Anything else a 0 anywhere? Bromine, that's right, on the product side. Whoops. Okay. What about sodium? What do you want to give sodium? What oxidation number? Saracen, it should be a +1. Yeah, sodium's a +1. Its oxidation number will match its charge as an ion. It's main group 1, so it's a +1. Okay, what about bromine here when it's matched up with sodium? What is bromine? -1, good. And then what is chlorine over here when it's matched up with sodium? -1. Okay, so we got everything assigned. So what's changing and how so? Zero to 1, +1. But we have a -1 on chlorine. Okay, so chlorine went from 0. I have a -1 on the product side. And then what else changed? Bromine went from -1 to 0. So what's oxidized? Yeah, bromine. And that means chlorine is reduced. Good. So you could do something like this and you'll be fine on the final. I'm not going to go find the hardest redox I can find. Okay. All right, I'm going to move on. Anybody have any questions about chapter 5? Do I have any more practice on chapter 5? No, that's all I had. So, and then remember a few weeks ago, was it a week or 2 weeks ago? Because James asked me, you can all thank James. I sent a bunch of worksheets, just practice types worksheets, okay? They didn't hit every single topic, but there was stuff on balancing and classifying reactions. If you want to practice, those worksheets were all attached in an email. So just search my name in your email or my email, and then you should be able to find those worksheets if you want to go through and practice more stuff like this. All right, chapter 6 was all about learning moles and mass and the relationship between those. So Avogadro's number, molar masses, things like that. All right, so we said when I introduced what a mole is, it's a unit. It stands for a number of items, just the way the word a dozen is a unit that stands for 12 items. Avogadro's number is a unit, a number that stands for a lot of items. Okay, 6.022 times 10 to the power of 23. That was Avogadro's number. So we said 1 mole of any substance is the amount of the substance in grams that's numerically equal to its formula weight and AMUs. All right. So for example, if I have hydrogen, all right, if we look at the periodic table, and I don't have one right here in front of me, but the number on hydrogen is 1.008. This is the atomic mass. Well, I should just write H, hydrogen. Okay. Hydrogen by itself, not H2. It does exist as a diatomic, but then its mass doubles. So we're just looking at a single atom of hydrogen. Its formula weight is 1.008 AMUs. But if I have this many grams of hydrogen, I have a mole of hydrogen atoms. That's what that's saying. Okay, and you do that for any substance. Okay. So after we introduced Avogadro's number and this idea of what a mole is and how it's the amount of that substance in grams means we have 1 mole of that substance, we started calculating molar masses, okay? So for example, calculate the molar mass of urea, which is CONH2 parentheses 2. How would we do that? We need to figure out how many of each kind of atom do we have. And that's pretty simple. The only time it's tricky is when you have these parentheses. This 2 means we multiply this by 2, and it means we multiply that by 2. So we have carbon, we just have 1 of those. Oxygen, we just have 1 of those. But nitrogen, we have 2 of those. And how many hydrogens do we have total? 4 of those, okay? So get the right numbers, and then you say times whatever its mass is on the periodic table. Carbon is 12.011. And so we're going to do this in grams because we're trying to calculate a molar mass, which is in units of grams. Oxygen would be 16. Nitrogen is like 14.0, I don't remember, 01. And hydrogen is 1.01 if you round, okay? So you multiply all of these up. And then we're gonna add all this up. So we wanna add all of this.
Gotten substantially better since taking this class.
Good. It has to. Chemistry definitely involves math. 28 and 28, 56. Is it 60.071? So that's how many grams are in a mole. So you can do that for any substance. All right. Then we can take something like a molar mass and we can use it to convert. You see how this is how many grams is in 1 mole. So we can use this to convert between grams and moles. So that's exactly what this problem, using molar mass as a conversion factor unit between grams and moles in the textbook, has you do. Active ingredient, milk of magnesia, which is an acid, is magnesium hydroxide, MgOH2. A typical dose, 1 tablespoon, contains 1.2 grams of magnesium hydroxide. There's 2 parts to this problem. A says calculate the molar mass of magnesium hydroxide. And then B, so I actually already did part A for you right here. Okay, 58.32 grams per mole. So B, we're just going to do part B. It says the amount of magnesium, calculate the amount of magnesium hydroxide in moles that's in 1 teaspoon. Okay, so one thing I'll give you that I would give you if this were like on an exam. Do y'all know how many teaspoons are in a tablespoon? 3, okay? Whoops. Sorry, that's incorrect. Okay, 3 of these. 3 teaspoons in 1 tablespoon. So how would you work this problem? I'm going to start with 1 teaspoon. Okay, this is the amount we're trying to figure out the equivalent in moles in 1 teaspoon. Okay, so I'm trying to convert to units of moles. How would I do that? Cancel teaspoons out. The only relationship I have to do that is the one I wrote right above, right? So we'll say for every 3 teaspoons, there's 1 tablespoon. Then what should I do? That's right, Kendall. So this problem tells me 1 tablespoon is equivalent to 1.2 grams of our substance. So for every 1 tablespoon, there's 1.2 grams of the MgOH2. I'm not to moles yet. I want to get all the way to moles. So teaspoons cancel, tablespoons cancel. Now what do I do? Do I? Molar mass. Cancel grams. So the 58.32 grams goes on bottom, and that's for every 1 mole of magnesium hydroxide. And then grams cancel. So somebody calculate this for me. You do 1, which is, just write it over 1 if you want, but 1 divided by 3 times 1.2 divided by, or times 1 over 58.32. What do we get? How many moles? Okay. Okay. It's a great little problem. Yeah.
I guess if they're large, it will be a scientific notation, but if they're small like that, we need to have a decimal like that, we have the scientific.
What would y'all prefer?
Personally, if it's small like that, I just want the decimal so I can say okay, that's the answer.
Yeah, to be honest.
Unless it's really big.
Right. Big numbers for sure be scientific notation.
That's just my preference. So I can still get my answer and look at that and not have to link.
Yeah. Just be ready for either way though. Okay, the next thing we did once we got comfortable with using molar mass to convert, just like what we did, is we applied it to chemical reactions. And we said we can do this thing, it's called stoichiometry. I probably didn't use that word very much in class, but that's what it is, where you're using mole ratios and you're using molar masses to figure out if I have, 10 grams of my reactant, how many grams of product could I form or something like that, okay? So this problem is a great example where we're going to use mole ratios and I think molar mass at some point. Okay, zinc metal reacts with hydrochloric acid. We actually did this in lab. You guys remember very beginning of the semester, we had little pieces of metal and we added hydrochloric acid to it, and you would watch it bubble, you'd watch it react. You were just trying to determine if a chemical change is happening or not, but you did this reaction, okay? So zinc plus HCl makes zinc chloride and hydrogen gas. That's the bubbling you saw. That was the gas that was being released. A says how many grams of hydrogen are produced if 15 grams of zinc reacts? How many grams of hydrogen are produced if 15 grams of zinc reacts? So we're going to start with 15 grams of zinc. What do I need to do? So it should be grams of zinc. The first thing we have to do is go to moles of zinc. Then we need to convert to moles of hydrogen. Then we can go to grams of hydrogen, okay? This is the 3-part problem. Step 1, step 2, step 3. We had a whole dry lab where you worked a bunch of problems like this at the end. You want to rework that dry lab. It's a great one to do. And now you have all the answer key on Blackboard to check yourself. All right, so the first thing I need to do is convert to moles of zinc. So for every 1 mole would be how many? Do I have a periodic table? Please tell me somewhere on this whole dang thing that I have. I don't. Anybody got one in your notes right by you? Okay, there's the molar mass of zinc. Now we need the mole ratio. So this was step 1, divide by the molar mass of zinc. Step 2, what is the mole ratio between zinc and hydrogen? 1 to 1. 1 mole zinc gives me 1 mole H2. That's really important. You don't forget that too. So this was step 2, plug in your mole ratio. Then for every 1 mole of H2, it's how many grams? It should be 2.016, I believe. So somebody calculate this. 15 divided by 63.38 times 1 times 2.016. What do you get? Okay. So that's part A, 0.46. Is that what y'all, everybody else got? Okay. Part B, what a great question. Is this redox reaction? If so, what's reduced, what's oxidized? Don't worry, I'm not going to ask you to identify reducing and oxidizing agents. I might ask you what's oxidized, what's reduced, sure, but. So what do y'all think? Is this a redox reaction or no? Did somebody say something? Elizabeth said, yes, it is. I agree with her. How do you know? Zinc, what's the oxidation number of zinc on the reactant side? 0. And over here, it's not 0. So yes, it is a redox reaction. Now we got to think a little bit more. And then hydrogen was not 0 on the reactant side, but on the product side, it does have an oxidation number of 0. What is reduced? What is oxidized? So what is the oxidation number of zinc when it's combined with chlorine? That's right, Jesselyn, +2. Okay, she said chloride, chlorine, chloride's got a -1. There's 2 of them. So zinc's got to be a +2 to match that and give you a neutral compound overall. So zinc goes from 0 to +2. Does that mean zinc is oxidized or reduced? Oxidized, that's right, Kendall. So hydrogen, real quick, we can look at that as a +1 becomes a 0. So hydrogen is reduced. Okay. So step 3. All right, I think that's pretty good practice with really the extent of what we did in chapter 6. There is one more problem if you want to practice it. It's just a great way to use. We have not yet used Avogadro's number in a problem. Did you have a question, Kendall? What's up? Not always. So for example, if you had you'd be tempted to look at this subscript right here and say, lead here is a +2, but it's not. Sulfate as a unit is a -2, and you've got 2 of them. So we have to say ×2, which means lead has to be a +4. So it does not always just match what the subscript is. But that's a good question. So I'll give you a tip on this problem. I'm not actually going to work it. It says the principal component of kidney stones. I have a family member, guys, who has had like 120 kidney stones. I'm not even kidding. They just had a procedure last Friday. They had 2 kidney stones in each kidney. It's just like, and they're on my husband's side. So I'm like, I hope this is not genetic in any way. It's insane. It's calcium oxalate. Okay. So have you ever seen a picture of a kidney stone? It's like a really hard. So you can imagine that's calcium oxalate. Okay. So kidney stone recovered from a typical patient contains 8.5 × 10⁻24 millunits. What is a formula unit? That should say molecules. Okay. But that was the wording from the textbook. So it's got that many molecules of calcium oxalate. How many moles of calcium oxalate are present in this kidney stone? All right. So because it's giving you the number of molecules and it's asking for the number of moles, you're going to have to use Avogadro's number here. Anytime it asks you how many atoms or how many molecules, or tells you a number of atoms and molecules, remember this chart where I said you can convert between grams and moles using molar mass, okay? We can go back and forth pretty easily, but to go to a number of molecules or atoms, you have to use Avogadro's number. And that's what you're doing here. It's giving you the number of molecules. That's where you start on this chart. It gives you that. And it's saying how many moles. So it's asking you to calculate that. So you have to use Avogadro's number. Okay. All right. Chapter 7 gets us to chapter 7, where we mostly talked about energy, delta H, delta G, reaction rates, reaction diagrams, how to manipulate rates with temperature or changing concentration, and then equilibrium and Le Chatelier's principle. Okay, so we're gonna be in chapter 7 for a few minutes. When we get close to 11, somebody shout at me so we can take a break. Okay, so the first thing we talked about was the law of conservation of energy, which essentially we said breaking bonds. This is not the law, but it kind of goes along with the law. Breaking bonds requires energy, and forming bonds releases energy in the same amounts. If I'm breaking the same bond that if you're considering the same bond and you're making or you're breaking it, the amount of energy absorbed or released is the same. Okay. If I make an oxygen bond, that's going to release the same amount of energy as if I break an oxygen bond. Okay. And that is what the law of conservation of energy says, that energy cannot be created or destroyed, just transferred, just absorbed, just released, transferred. Okay. So then to understand this, we said there's 3 pieces to the puzzle: enthalpy, entropy, and Gibbs free energy. And these all come together in that mathematical equation for delta G to give us the full picture. All right. But first we talked about enthalpy. which is delta H, okay? You are not going to have to, I think in previous semesters, I have had people calculate delta H. You're not going to have to calculate delta H. We really didn't, I think we did it one time, but I have not had it on any exams or anything like that. So I may give you a delta H and I want you to know what that means. Or I may tell you energy is released in this reaction or absorbed in this reaction, and I want you to know what that means, but you're not going to have to calculate, okay? So speaking of endothermic and exothermic, those were the overall summary words that I gave you guys so that you could look at a reaction or look at a given delta H or read a problem and determine if energy is being released or absorbed. So endothermic reactions, what kind of delta H do endothermic reactions have? Yeah, these have a positive delta H overall. So that means exothermic reactions have a negative delta H, okay? Now I'm going to come over here in endothermic. If you're absorbing energy, let's pretend we are the chemical reaction. Put yourself like, you have to view it from the viewpoint of the chemical reaction. If you're absorbing energy, are you left in a state that's more stable or less stable? Less stable. The more energy you absorb, the less stable you become. Okay, so the products here are less stable. You're absorbing energy overall, positive delta H. But in exothermic, you're giving off energy. You're releasing energy. The chemical reaction is losing energy. That leaves you with products that are more stable. Okay. All right. That's really all I'll get into with enthalpy. I think do I have some practice problems maybe? No, we'll see. I think I do. When determining the sign of delta S, so the next part is entropy, which is delta S. Entropy, change in entropy is delta S, okay? So one thing we did with delta S is we look at a chemical reaction, say, is the delta S positive or negative? Is entropy increasing or decreasing? Now remember, what is entropy? It's a measure of what? It is a measure of disorder or disorganization, which I need to write somewhere on this slide. So delta S is a measure of disorder. And before we answer or fill in these two blanks, we talked about solids, liquids, and gases. Okay. We said that which state of matter is the most disordered? Gas, okay? Gases are most disordered. Okay, solids are much more ordered, liquids are in the middle, gases are inherently most disordered. All right, so when determining the sign of delta S for a reaction, you must consider what? You must consider, what's the best way I want to phrase this? I'm just going to write your states of matter. What I mean by that is you need to assess. In this reaction, am I making solids or am I going from like a gas to a liquid? What's the transitioning that's happening? Do I have gases on the reaction side and gases on the product side and then really can't consider if things are becoming more disordered or less disordered from states of transition or states of matter? So think about what states of matter your reactants and your products are. Okay. And then also we said, consider the number of moles. Of reactants or products. Okay. as you go from reactants to products, are you making more moles of stuff? Is this a decomposition reaction? Is it a combination reaction where you're making fewer moles of stuff on the product side? Okay. My favorite analogy is like, consider a decomposition reaction. You got one reactant making two products. Okay. Which one's more disordered? Dealing with one kid or two kids? Okay. Those are easy ways to tell, counting the number of moles of reactants or products. Okay, and then once we understood delta H, and then once we talked about delta S, we said these two things come together to give us the overall picture, which is summarized with delta G, okay? So we learned how to calculate delta G from delta H and delta S. And the equation that we had for this is right here. Delta G equals delta H minus T delta S. Delta G equals delta H minus T delta S. And so if you're asked to calculate delta G on the exam, very good chance that will happen. You can kind of count on it. What are two things? What was that name? Yep, so that's what we're going to fill in here. Two things to check before you calculate delta G. Nay just said one is the temperature needs to be in Kelvin. So convert it to Kelvin if it's not. Number two is what? What else do we have to check before we just plug our numbers in? Remember? Units on delta S need to match the units of delta H. So I always just take my delta S. Usually delta S is calories or joules per mole Kelvin, and convert it to kilocalories or kilojoules for delta H. This is because changes in delta S are always just way smaller than changes in delta H. That doesn't mean they're not important, but it's always easier to track them with smaller units. But if we're gonna plug them into the same equation, they need to have the same units. Okay, and then once we calculated delta G, we can say, okay, our reaction is endergonic or exergonic. What means what? Positive delta G, negative delta G. Do you guys remember? Endergonic is positive delta G. Exergonic is negative delta G. Now, which one's favorable? Which one is spontaneous? What did you say, Keely? That's right. Okay. Negative delta G, this one is spontaneous or favorable. Do you remember the combination of delta H and delta S that always gives you a negative delta G? This is one table you will not have on your charts, okay? Or on your exam resources page. We said negative delta H and positive delta S always give a negative delta G. So that combo is favorable. The opposite of that, positive delta H and negative delta S always give a positive delta G, which is never spontaneous. Okay. Wow, I have a lot of slides on chapter 7. Okay, so now that we've discussed this, let's work a problem just as review. After this problem, we'll take a break. The following reaction is used in the industrial synthesis of PVC, polyvinyl chloride. So look at this reaction. Is delta S positive or negative for this process? I give you the delta H, it's negative. So what do you think? You've got chloride, which is a gas, plus this CH2, ethene, I guess is what you call that, and make PVC. What do you guys think? Which is a liquid? So is disorder increasing as you make your product or decreasing? And so it's not increasing. You'll agree? Okay. So that means delta S is, disorder is decreasing. So delta S is negative. You're going from gases, making a liquid. You've got 2 reactants and only 1 product. There's several ways you could look at that. So you're becoming more ordered, which means disorder is decreasing. So is this process spontaneous at all temperatures? Explain. So what we have is a negative delta H, and we also have a negative delta S. So we consider this is our equation overall. Okay, so we have a negative delta H, we have a negative delta S. When the signs are the same, it really depends on temperature. If you have a negative delta H and a positive delta S, yeah, spontaneous at all temperatures. You'll always get a negative delta G. If you have a positive delta H and a negative delta S, nope, never spontaneous at any temperatures. So I guess the question here is no, it's not, or the answer here is no, it's not spontaneous at all temperatures. But how would we explain that? Depends on the temp. Okay, at higher temperatures, so T times delta S is going to be negative, right? Because delta S is negative, and temperature is always positive. You can't have a negative Kelvin. But then this negative out front times that is going to make this whole unit positive, because negative times negative is positive. So the higher your temperature, the more likely at high temps, this whole term will outweigh your negative delta H. It would be bigger. The higher temperature. So at high temps, we'd have positive delta G. And at low temps, we'd end up with we're more likely to have a negative delta. So it's more likely to be spontaneous at lower temperatures, non-spontaneous at higher temperatures. Okay. All right, let's take a 5-minute break and we'll resume at 11. I'll be right back. All right. What's up, Elizabeth?
If we just said no, it just depends on the temperature, would that be okay? Or do we
Well, remember, pretty much all the questions are going to be multiple choice. I realize I'll probably have some balancing chemical reaction stuff. Remember, like on exam 2, where you'd like balance the reactions, and that's not actually multiple choice, but it's just like fill in the blank type stuff. So you're not going to have to actually shorthand write anything out. You'll be picking from a selected list of answers. Does that help? Yeah. Okay, you all ready to go? I mean, like finish. I know you're ready to go. Who wants to be inside on a day like today? Okay, chapter 7, we're going to talk about reaction rates and then equilibrium and maybe Le Chatelier's principle. See, Kendall. Okay, so here, what determines how fast or slow a chemical reaction will occur? That's the next topic we assess after assessing energy in delta G. And we said the activation energy on an energy diagram essentially determines how fast or slow something will be. Okay, so you got an energy diagram like this, and here's your energy level of your reactants, and you've got some sort of energy peak, and the difference between the reactants and the top of that peak, we said this is your activation energy, which actually I abbreviate EACT. So if that's a really big peak, then it will be a slower reaction. But if it's a really low peak, so for example, I could draw another diagram where maybe I have a smaller activation energy. And so this one would have a lower activation energy in the black. So this reaction would be faster. And in the red, whoops, it would be slower. Okay. So make sure you can look at an energy diagram, label the energy level of the reactants, the products, the activation energy, the delta G. So the delta G, let me change colors here, is always the difference between the energy level of the reactants and the products. Okay, so you want to determine where's the energy level of my reactants, where's the energy level of my products, and the difference between the two is your delta G. Delta G doesn't really have anything to do with the activation energy. Okay. So that's energy diagrams. And then we said there's 3 ways to manipulate reaction rates or increase them. If we increase the concentration of the reactants, you increase the rate. You increase the frequency and the forcefulness of the efficient collisions. And then if you increase the temperature, you can increase the reaction rate that way. And if you add a catalyst, it'll overall increase the rate because you're lowering the activation energy by bringing the reactant molecules close together in proper orientation. So these are ways to increase, not just manipulate, but increase reaction rates. This would be either endergonic or exergonic. Yeah. So you could, I mean, I very well could ask you, is this endergonic? I did on exam 3.
That's what I was asking.
Yeah. So this would be a negative delta G, meaning exergonic. Do what? What would positive delta G look like? If you had a chart like this, and reaction or reactants, and here's your energy peak, and then your energy level of the products is higher. So as you go from reactants to products, you have to go up, right? And so this would be a positive delta G, endergonic. Less stable. Products are higher in energy. Okay. Chapter 7 continued. Last topic here, I think, unless I have, yeah. Le Chatelier's principle. Last two slides. So then we talked about equilibrium. What happens when your delta G is close to 0? Okay, and you have forward and reverse reactions happening at the same, I'm going to highlight this word, rate. Okay, equilibrium is all about equal rates. That does not mean you have equal concentrations of reactants and products. That means you have a reverse reaction happening at the same rate as your forward reaction. Okay, so then we practice writing out an expression or an equation for K, your equilibrium constant, and then predicting if reactants or products are favored. So remember, K always equals the concentration of products over the concentration of reactants. And you exclude things that are solid and things that are liquid, okay? You only include things that are aqueous and things that are gaseous. Okay, so 7.53, right beneath here. For the reaction, N2O4 makes NO2. So I did this as a demo in lab. I had that vial of brown gas. You guys remember I put the vial in the hot bath and I put the vial in the cold bath, and we saw how the brown became more intense or less intense in the vial. This was this reaction, okay? So it tells you concentrations at 25 degrees Celsius at equilibrium for NO2 are 0.0325 molar, and for N2O4, dinitrogen tetroxide, 0.147 molar. So let's calculate K. What's the value of K? Are reactants or products favored? So what would we write? We'd say K equals, both are gases, so I can include both. And remember, you raise things to the power of their coefficient. So we'd say product is NO2. I'm just going to write this in first so that we can make sure we plug everything in right. And then N2O4 needs to go on the bottom, and we're going to square the concentration of NO2. So when we plug numbers in, K becomes 0.0325 squared over 0.147. So you do 0.0325 squared divided by 0.147. What do we get for K? Okay, so this is less than 1, right? It's a decimal. So are reactants or products favored? Remember that color-coded arrow? The blue and the orange and the red and the purple arrow? If K is less than 1, reactants are favored. The last big topic in chapter 7 was Le Chatelier's principle. Which says when stress is applied to a system at equilibrium, and that stress could be changes in concentration, changes in pressure, changes in temperature. It says the equilibrium concentration shifts to relieve the stress. They try to reestablish equilibrium by either making reactants or making products. All right. So our changes, like I said, could be changes in concentration, temperature, or pressure and volume. So how do these shift? We're going to kind of come up with maybe a key here that can help us. If the change is an increase in the concentration of reactant, I'm going to put an R for reactant. Remember, brackets indicate we're talking about concentration. An increase in concentration of reactant means equilibrium will shift which way? You guys remember? It would shift right towards products. But a decrease in the concentration of reactant means equilibrium will shift. I'm just going to draw arrows now. Left. To try to replace the reactant, the amount of reactants that was taken away. Okay, what about products? If we increase the concentration of product, equilibrium will shift left. If we decrease, that would be towards reactants. But if we decrease the concentration of product, equilibrium will shift towards products. This way it would shift right. Okay, what happens with changes in temperature? It depends if your reaction is endothermic or exothermic. Okay, if it's endothermic, meaning positive delta H, do we consider heat to be a reactant or a product? Positive delta H means heat is a reactant. I'm just going to put R for reactant. So a negative delta H means heat is a product. So for endothermic reactions, if we increase in temp, heat's a reactant here, means it would equilibrium would shift towards the product side, shift right. But decreasing temp, so I'm just going to put a down arrow, decreasing temp, equilibrium will shift back towards the reactant side. If it's exothermic, heat's a product and you increase temp, equilibrium, I'm just going to draw arrows now, will shift towards the reactant side. And if it's an exothermic reaction and we decrease temperature, equilibrium will shift towards the product side to replace the heat that we're taking away. Okay, that looks so crazy looking at it. I feel like we're writing in code right now. Guys, we listen to this podcast. It's called The Agent. On a long trip, I really suggest it if you listen to podcasts. It's about a guy who grew up in Germany, and then he started working for the KGB, the Russian, it's basically the FBI, but like for Russia. And this is like back in the 60s. So a lot of the stuff they were doing is like totally not possible now. It's his whole life story. It is insane. Like how he made it to the United States. We were considered the enemy. How he had this fake identity. How he lived here. Like, I don't know why. When I said the word code, it made me think of that podcast. It's called The Agent. Yeah, it's on Spotify. We looked to it on Spotify. Okay, back to our code. Changes in pressure. So here I'm not going to draw these arrows or as many, but you have to first, so the first thing you want to do, step one, is count how many moles of gas are on each side of your equation. Okay, so count how many moles of gas are on each side, figure out which side has more moles of gas, fewer moles of gas. Because here's what happens: an increase in pressure, equilibrium shifts to the side with fewer moles of gas. And a decrease in pressure, equilibrium shifts to the side with more moles of gas. Okay.
Not so simple like this. It makes a lot more sense.
Well, maybe I should do this during lecture when I first introduce it. That would help. I'm gonna remember that.
Like this.
Like that?
A lot of arrows, but like have them fill in.
It's
do arrows themselves for a station.
Okay.
It's a real good. It's like a really good visual.
Okay, good. I'll remember that. We're gonna try that in the fall. Okay, that gets us to chapter 8. But I do suggest practicing a problem in the textbook now that we wrote all that out with equilibrium or Le Chatelier principle. Okay, gases, liquids, and solids. So 2 chapters. Let's push through these. So we worked on understanding 1, the intermolecular forces between molecules that are solids, liquids, and gases, and then the amount of kinetic energy associated with each state. All right. So we said that solids are interacting a lot. Those molecules are close together. So high amounts of intermolecular forces. Gases, the molecules are really spread apart. They're not really interacting at all. So low amounts of intermolecular forces. Okay, so solids have high amounts of, I'm just going to write IMFs, intermolecular forces. Gases have low amounts of, or no IMFs, no intermolecular forces. But solids have low, I'm going to write KE, kinetic energy. They're not really moving very fast, but gases have very high kinetic energy. And then we said, okay, how arrangement energy changes when matter undergoes transition between the phases. So for example, we had a diagram in chapter 8, very first slide in chapter 8, after my hiking pictures, that had like changes between solid, liquid, and gas, melting, freezing, thawing, condensing. And we could label every single one of those with a positive or negative delta H. Okay, so for example, melting. Melting implies that you're going from a solid to a liquid, right? Is heat being absorbed or released? Is this a positive delta H or a negative delta H? It's being absorbed, so we say positive delta H. Condensation means you're going from a gas back to a liquid. When you see condensation form on a glass outside in the summer or on a window. Okay, so here heat is being released, so that would be a negative delta H. Okay. Sublimation is a solid directly to a gas, dry ice. And that would be a positive delta H. Okay. That was weird. Okay. The next thing we talked about was intermolecular forces, 8.35. I have next slide on here. Oh, we'll do a practice problem in the next slide. So we talked about London dispersion forces, also known as van der Waals. These are the strong. They occur in all molecules. So I'm just going to write that they're present in all molecules, but they are the strongest in non-polar molecules, because non-polar molecules cannot have dipole-dipole interactions. They cannot hydrogen bond.
I don't know why, but I remember it's van der Waals.
That's fine.
Have both on there, like both.
Oh.
Just have one or the other. I mean, I can.
Probably just one or the other. Dipole-dipole forces, these occur in polar molecules. Okay, so London dispersion, those are van der Waals. These are temporary dipoles. We said they're here for a split second and gone. That's what creates the intermolecular force. But a dipole-dipole interaction is a permanent dipole. Polar molecules have permanent dipoles. They orient themselves like this. If we have one molecule where this side is partial positive and this side is partial negative, on the neighboring molecule, they'll line themselves up so that the opposite semi-charges are interacting, okay, are attracted to each other. They sense that separation of charge. Bless you. Okay. Hydrogen bonding requires two things. So this is the strongest intermolecular force that we talked about, and it requires a donor, okay, which is a partially polarized or a positively polarized hydrogen, and it requires an acceptor, which is the lone pair on an oxygen, or the lone pair on a nitrogen, or the lone pair on a fluorine. Now, to hydrogen bond with like a water molecule or something like ammonia, you just need to have a donor. No. If all you have is an acceptor, you can still hydrogen bond with a neighboring molecule. But to hydrogen bond with yourself in pure form, you got to have a donor and an acceptor. Okay. To hydrogen bond in pure form, you need to have a donor and an acceptor. You just have, because you can't have a donor without also having an acceptor. Okay, because these are, the donor is a, I guess I should scoot this over. The donor is partially polarized or positively polarized because it's bonded to an oxygen, nitrogen, or fluorine. Okay, so there's no way to have a donor on your molecule without also having the acceptor. But if you just have an acceptor, then you can still hydrogen bond, but just not in pure form. And then we talked about all these and we said, let's also understand how these forces influence melting points and boiling points. And we practiced ordering molecules. That was a problem on the exam 3. Yeah, exam 3, according to increasing or decreasing melting points or boiling points, okay? So if I give you a molecule that's nonpolar and it has London dispersion force, if I give you a molecule that's polar and it can have dipole-dipole IMFs, or I give you a molecule that can hydrogen bond, the one with the highest melting point or boiling point would be the one that can hydrogen bond. The stronger those molecules are held together, because stronger intermolecular forces are present, the higher the melting point or the boiling point is going to be. Okay, but the weaker the forces are holding molecules together, the easier it is to melt or vaporize. So we had this problem here. This was straight out of our lecture notes too. I'm not going to sit here and work every single one of these. But for example, let's do this one. Let's do this one. And let's do this one. Okay, so A, nitrogen. If you want to draw this out, you got a triple bond. You got lone pairs here. What kind of molecule is nitrogen? Is it polar or non-polar? That's the first thing you want to decide. That's right. It's non-polar. So the type of force it can interact with is London dispersion or van der Waals forces. That's the type of intermolecular force those molecules would have. HCN. What do you guys think about this molecule? you would need an electronegativity chart, which you will have. But when you look at that, you'll find out that this bond between carbon and nitrogen is polar. Carbon's partial positive, nitrogen's partial negative. So it's got a permanent dipole, which means it will have dipole interactions. NH3 looks like this. What kind of an intermolecular force do you think ammonia here would have? Hydrogen bonding, because we have hydrogens here that are directly bonded to nitrogen. All of these hydrogens are positively polarized. And then we also, so these are all donors. And then this lone pair here is our acceptor. So great question. Why can HCN not hydrogen bond? The hydrogen is not directly bonded to the nitrogen. It's bonded to carbon. So we would not call that hydrogen positively polarized. This carbon-hydrogen bond is non-polar. The electronegativity difference is not large enough. Now, HCN could hydrogen bond with like a water molecule, but if we're considering these in pure form, then HCN can only have dipole-dipole interactions, cannot hydrogen bond. So if I ask you which one of these, A, B, or D, had the highest boiling point, you'd say ammonia has the highest melting or boiling point. And which one would have the lowest? Nitrogen would have the lowest boiling point. Okay. I forgot what it's like to lecture for 2 straight hours. That's what I do in summer. Anybody ever had summer class? It's just like you go, 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 go. Okay. So that's intermolecular forces. Then the back half of chapter 8 was all about gases, gas laws. So we said we can measure gases mostly using pressure, volume, and temperature. And we said there's lots of units for pressure. So 1 atm, you'll have all these numbers on the exam. 760 millimeters mercury, 14.7 psi, 101.325 pascals. So you may have to convert. The biggest thing here is that in a gas law problem, if I give you 2 different variables for pressure, you got P1 and P2, you make sure those units are the same before you just plug them into the gas law, okay? Now, if you're working with the ideal gas law, you want to make sure that your pressure is in ATM. It needs to match the units on the gas law constant R. But otherwise, you just want to make sure that they match if you're doing a combined gas law problem, which is what we have here, 8.63. A compressed air tank carried by scuba divers has a volume of 6.8 liters and a pressure of 120 atm at 20 degrees Celsius. What is the volume of air in the tank at 0 degrees Celsius and 1 atm pressure? So let's just go through and label. Here's a volume that we're given. This must be V1. Here's the first pressure that we're given. So this is P1. And then here's the first temperature. This is T1. We're then given another temperature, T2. This should be 1 atm is P2. And it's asking for V2. So our equation, you'll have this on your chart at the end of the exam, is P1 V1 over T1 equals P2 V2 over T2. We're solving for V2, so let's rearrange our equation. I want to cross multiply by T2 and cross divide by P2. So that will all cancel on my right side, and my new equation is T2 over P2 there's my equation. change to Kelvin. Always change them to Kelvin. So 20 degrees Celsius. Just go down here, 20 degrees Celsius plus 273.15 is 293.15. And then 0 degrees Celsius is equivalent to 273.15. So we got our temperatures converted, and pressure is in ATM. So we're good there. So now we just plug everything in. So we'll have T2, which is the 273.15 over P2, which is 1 ATM, times P1, which is 120 ATM, times V1, which is the 6.8 liters, over T1, 293. So somebody work this out for us. What do we get? Anybody got it? 760.3 liters. So a lot of gas, a lot of air. We're doing some deep scuba diving. That freaks me out. I don't think I could ever like go deep down the ocean. Okay. All right. Ideal gas law, and then we're on to chapter 9, the last chapter. So ideal gas law, you'll have this constant 0.0821. Just pay attention to the units when you're doing an ideal gas law problem. It's liters times ATM over mole times Kelvin, right? So if we're working ideal gas law problem here, this is 15 grams of CO2. Gas has a volume of 0.3 liters at 310 Kelvin. What's the pressure in millimeters mercury? I'm gonna say an ATM. I don't want to do that much work. Don't you wish you could edit a test like that? So PV equals nRT. You'll go find that equation. We're trying to solve for pressure, so you want to cross divide both sides by V, so you get P equals nRT over V. So the first thing we need to do is convert grams of CO2 here to moles. 15 grams of CO2, we need the molar mass. How many grams are in 1 mole? So carbon is 12.01, oxygen is 16 times 2 is 32 plus 12, 44. Okay, so we're gonna, somebody throw this in your calculator. 15 divided by 44, it should be roughly 0.3. 0.34? Okay. Moles. So now that we have moles, which is our variable for in the number of moles, now we can plug everything in, and our units are good on everything else. Volume is in liters, temperature is in Kelvin. You want to check those things. Now we just plug it all in. Pressure is equal to 0.34 moles times R, 0.0821 liter times ATM per mole Kelvin, times temperature, 310 Kelvin. Divide that all by 0.3 liters. What do you get? No sugar? Okay. All right, on to chapter 9. Any questions on chapter 8 stuff? Can you believe we're doing it? We're covering online chapters in 2 days. Did you think it was possible? All right, chapter 9 sometimes reminds me of chapter 7. There's just so many little topics that we covered. First one was understanding the difference, understanding what a solution is and the difference between a solution and a colloid. So a homogeneous mixture, that's what a solution is. And we said that a solution has smaller particles. This is the main difference. Whoops. Smaller particles, like particles that are smaller than 2 nanometers in size. Whoops. Nanometers really small, right? So smaller than 2 nanometers in size. Colloids have larger particles. Milk was an example of a colloid. What is in milk? Fats, proteins, sugars, all in milk. So it's got larger stuff in it. So colloids have larger particles. Then we identified the parts of a solution. We said the solute is what is dissolved in the solvent. Solvent. Always like I don't have the best finding it. It's just what's dissolving the solid. Present in greater amount. Okay, but then once we defined all these parts of a solution, we said, okay, let's look at how solubility works. How do we know if we mix 2 things that we'll get a solution? Maybe sometimes they won't mix. It all depends on this phrase that we said, like dissolves like, which hinges on intermolecular forces, understanding if things are polar or non-polar, and understanding if you have similar types of intermolecular forces between your solute particles as your solvent particles, or if they're different. Okay, so we said polar and ionic solutes dissolve in polar solvents. And then nonpolar solutes dissolve in nonpolar solvents. But we said polar or ionic does not dissolve in nonpolar. And vice versa. Nonpolar stuff does not dissolve in polar solvents. Okay. After we discussed this and worked a few practice problems on it, we started to look at the effects of temperature on solubility. So we said solids become, I guess my blank here is more soluble in a liquid as temperature increases. But we said gases become less soluble in a liquid as temperature increases. Okay, so for example, if I have sugar or salt and I put it in hot water, the solubility increases. I can probably dissolve even more sugar or salt in hot water than I could in cold water. Okay, but think about a gas in a liquid, a carbonated drink, CO2 dissolved in that liquid. The gas is more soluble when the liquid's cold. Okay, it's less soluble when the liquid's hot. It's really hard to get gases dissolved in hot liquids. And it's flat, yeah, no fizz. But you take it out of the fridge, it's really cold, then it has a lot of CO2 dissolved. Now there's pressure involved there too, because those cans are pressurized. But in general, gases become less soluble as temperature increases. Solids become more soluble in a liquid as temperature increases. This led us to Henry's law. So gas solubility increases as pressure increases. Henry's law, C1 over P1 equals C2 over P2. We just had a problem like that on exam 4. So there, you know, I would give you 3 of the 4 pieces and you're just solving for the 4th or missing piece, okay? C stands for concentration or the solubility of the gas, the amount of gas in the liquid. P is the pressure. And you, again, you want to make sure for P1 and P2 that you'd have like similar units. Any unit is fine as long as P1 and P2 have same units. Okay, after that, we got to concentration, units of concentration. So weight, volume, percent, or molarity. And molarity, I should say. We discussed both. So let's work a weight, volume, percent equation. It says the concentration of glucose in blood is approximately 90 milligram per 100 ml. What is the mass volume percent concentration of glucose? And what is molarity? Okay, so, and I should also write molarity up here. These are the 2 we looked at. So we're going to do both. So it tells us that the concentration is 90 milligrams of glucose and about 100 milliliters of blood. And it wants to know what's the mass volume percent. Okay, so mass volume percent equals grams of solute here, which is glucose. Glucose is what we're saying is dissolved or in our blood per milliliter of solution, which is the solution here is your blood. So what do we need to do to figure this out? We have 90 milligrams per 100 ml. That's not quite mass volume percent. So let's take those 90 milligrams of glucose. That's the substance we're talking about. Let's convert that to grams, right? There's 1,000 milligrams in 1 gram. So what this means is we have 0.09 grams dissolved in 100 milliliters. 90 milligrams is 0.09 grams. Now we can plug this into our equation for mass volume percent, which would be 0.09 grams of glucose over the 100 milliliters of solution. Now we'll say times 100. So our mass volume percent is just, don't calculate it, the hundreds cancel.
I'm sorry.
You're good, you're good. I want to help you recognize these things though, because these would be shortcuts on the exam that would save you time. Just notice those hundreds cancel. My percent is 0.09%. But what's the molarity? Okay, so how would we get molarity out of this information? Molarity is what? It's moles of solute over liters of solution. So molarity, we need moles of glucose. We have grams of glucose. We know it's 0.09 grams. We need to convert that to moles. So we'll take our 0.09 grams of glucose. The molar mass is 180. I would give this to you. I think it's 156 or something like that. Those decimals might be off. Per 1 mole. I do know it's 180. So somebody take your calculator, do 0.09, divide by the molar mass. How many moles is that? Okay. And then we need to know liters of solution. Well, all we know about the solution is that we've got 100 milliliters. This is the amount in 100 milliliters. So we need to convert that to liters. And then we just do moles divided by liters, right? So 100 milliliters divide by 1,000, we should get 0.1 liters, okay? So the volume is 0.1 liters. The moles is 0.005 moles. So we'll come back up here and we'll say molarity equals 0.0005 moles over 0.1 liters, what is our molarity? Okay, so 0.09% and 0.05 molar. All right. Okay, I think we just have 2 slides left and that's it. So the next big topic in chapter 9 was using molarity as a conversion factor. So problem 9.6 is a great example of this. This was kind of very similar to the 3-part problems we did in chapter 6, where you're going to be given like a volume. And this is how you work a titration problem too. You're given a volume, you convert that volume to liters, then you use the molarity to convert liters to moles. Then you plug in a mole to mole ratio. Then you plug in another molarity to go back to volume if it's asking you how many milliliters, okay? So this is if you have solutions of stuff in your reaction and you're trying to figure out what volume of this solution I need to react with this solution to get my products or whatever it is. So it says sodium thiosulfate, the major component of photographic fixer solution. This must be back in forever ago because we don't develop pictures like this anymore. I don't know, maybe diehards do. Reacts with silver bromide to dissolve it according to the following reaction. Okay, so it gives you this reaction. It's kind of confusing. These are your products. I think for space purposes, it just did not write those on the other side of the arrow. So this is how many moles of sodium thiosulfate would be required to completely react with 0.450 grams. You know what? I actually don't want to do part A. I just want to do part B because part A is like chapter 6 stuff. So how many milliliters of 0.02 molar solution of sodium thiosulfate contain this number of moles? Oh, dang. We have to do part A to do part B. So what is the molar mass? I'm going to do part A real quick. We're just going to get our answer and then we're going to work part B together. So I need the molar mass of silver bromide. Which is 187.77. And then AGBR2, so that's a times 1 to 2, so it's a times 2. Okay, so our answer is 0.00. I'm going to say 5. All right, so we're going to start with 0.005 moles of the Na2S2O3, okay? And it says how many milliliters of 0.02 molar solution contain this number of moles. So if we need 0.05 moles to react with our silver bromide, which was from part A, how many milliliters of a 0.02 molar solution contain this number of moles? So what is molarity? Molarity equals moles over liters, right? Now in the end, we'll convert to milliliters. But what we're going to do is we're going to take this number of moles, we're going to plug in our molarity so that moles cancel. So it's 0.02 moles per 1 liter. That's what a 0.2 molar solutions mean. We're plugging in the molarity here. We're separating out the mole and liter terms, okay? That's what this capital M up here means, mole per liter. And moles cancel, and we're going to get a volume. So 0.005 divided by 0.02, we should get 0.240. I actually rounded this answer to 0.005. So if you get something slightly different, but this is how many liters if you don't round that answer. And then it says how many milliliters. So we just want to convert this to milliliters, right? So for every 1 liter, it's 1,000 milliliters. And we'd say 240 milliliters. Okay. Any questions on that? All right. Last slide, then we're done. So the other few equations we hit in chapter 9, dilution problems, M1V1 equals M2V2. So there, just make sure your volume is like both in milliliters or both in liters. Okay, that your concentration's in molarity. And you solve for the piece you're missing. You'll be given 3 of the 4 pieces and you solve for the piece you're missing, okay? Electrolytes. We talked about how there are strong electrolytes. How do you recognize a strong electrolyte? This is something, for example, HCl, one-way arrow, one direction to products, something that breaks up into ions, disassociates, and you end up with all product. Or in other words, all ions, because your product is ions, or are ions. That's a strong electrolyte, something that completely ionizes, is what we would say. Completely ionizes. A weak electrolyte would be something like a weak acid is a really good example. So acetic acid, CH3COOH. You're going to get a double arrow here. So it will only partially ionize into here, CH3 and COO minus acetate and hydrogen. Okay, so a strong electrolyte completely ionizes. A weak electrolyte partially ionizes. A non-electrolyte doesn't ionize, doesn't make ions. That would be when you have molecules like glucose as a solid, okay, like melting into their molecules or whatever. Okay, we'd represent the reaction like this, but nowhere in that does glucose break apart into ions. So you get no ions, okay? Fructose, sucrose, hormones would be molecules that we do not consider to be electrolytes. Okay, last thing. Oh, you know what I don't have on here is equivalence. So I'm just gonna make one quick note of that up at the top. Equivalence. This is the, so one equivalent is the amount of ions that contain or creates 1 mole of charge. How do I want to write that? One equivalent equals the number of ions that makes 1 mole of charge. Okay, the number of ions that gives you 1 mole of charge, plus charge or minus charge, that's 1 equivalent. So if you have 1 mole of sodium cations, that's 1 equivalent. If you have 2 moles of sodium cations, that's 2 equivalents. If you have a mole of sodium chloride, you'll end up with 1 mole of sodium cations and 1 mole of chloride anions. That would be 2 equivalents, because the sodium would be 1 equivalent and the chloride would produce another equivalent. Okay, so with compounds, you just break them up into their ions, multiply the charge by the number of moles you have, or molarity, and add up your total equivalents that way. Okay, osmosis and osmolarity. So osmolarity, I did not leave space to define this. This is the number of particles per mole, or sorry, per liter of solution, okay? So again, how do you define a particle? You're not looking at charge here. You're just considering, do I have a substance that breaks apart into like ions or not? Let's go back to what we were talking about with equivalence. If I have 1 molar of HCl, What's my osmolarity? This is going to break apart into how many particles? Yeah, I'm not focusing on the charge here, but 1 particle and 2 particles. So I'd have 2 osmoles. Now, if I have 1 molar glucose, what's my osmolarity? 1 osmole, because it doesn't break apart into particles. It is the particle, okay? All right, then we defined isotonic, hypotonic, and hypertonic. Isotonic is solutions that have the same osmolarity. Hypotonic means lower osmolarity. Hypertonic means higher. Solution with higher osmolarity. So solvent, when we're talking about how osmosis works, solvent moves across semi-permeable membranes from solutions that have a lower osmolarity towards things that have higher osmolarity. That's how they flow. And we talked about red blood cells. If we took them and placed them in pure water, the question here is, why do red blood cells swell up and bust when placed in pure water? Because all of a sudden there's a gradient. Inside that red blood cell, if we draw this, you have a higher osmolarity. This is your RBC here, okay? And in the surrounding water, which is outside the cell, you have a lower osmolarity. So solvent is going to move from lower osmolarity to higher osmolarity. That's how it's going to move. And it would cause that cell to swell and eventually bust. That is the end of our final exam review. Thanks for coming. If you have questions, I'll stick around. But I am going to shut off the Zoom real quick.